Today I'm going to present the problem number 15, Newton's Cradle. So, problem to be investigated. The oscillation of a Newton's cradle will gradually decay until spheres come to rest. Investigate how the rate of decay of Newton's cradle depends on relevant parameters such as the number, the material, and the alignment of the spheres. So, first of all, let's define what is a Newton's cradle, okay? Newton's cradle is a device that demonstrates the conservation of momentum and energy using an alignment of shrinking spheres. In Newton's cradle, the potential energy that the first sphere has will change form and end up as kinetic energy to the last one. Here you can see an image, basically that demonstrates this investigation. So, by the way, in addition to this, an ideal Newton's cradle with 5 spheres where there are no energy losses and there's always a small separation between the objects except for when a pair is colliding. Operation of the alignment. First, one of the end balls is pulled sideways. Second, it is let go to follow an upward arc. The string in which it's attached makes the following arc, and third, it strikes the next sphere and immediately comes to a dead stop. Fourth, the next sphere strikes the following and transfers its momentum. 5, and finally, the sphere on the opposite side acquires most of the velocity of the first ball and swings in an arc almost as high as the relief height of the first ball, which means that there's a conservation of energy. Of course, that demonstrates that the last ball receives most of the mechanical energy and momentum of the first ball. The impact produces a compression wave that propagates directly to the means of propagation through the intermediate balls, as it's being demonstrated. Now, the theoretical explanation of the phenomenon. First, the kinetic energy of the system is transferred through the balls after they collide, and it remains constant. Since their masses are equal, which is very important to know that, the velocity of the moving ball remains the same. In real life, though, cradle isn't totally isolated because of friction, inelastic collisions, air resistance, and other parameters too. Now, here is a description of the law of conservation of momentum that describes that. Where P is defines momentum and mass, V velocity, and the last one is kinetic energy. Now, what are the parameters? All the spheres are ideally exactly the same size, mass, and density. Different sized spheres will still perform likewise, but will make the demonstration of the physical principles much less clear. In other words, we will have some discrepancies between the results that we will extrapolate due to the fact of different measurements because of the different size, mass, and density that will give us different results. Also, the spheres must be perfectly aligned at the center of the mass in order to make the cradle work the best. If the spheres hit each other at some other point, but the center of mass and energy momentum is lost by being sent in a different direction. Here can be seen that this is perfect alignment. So it's the perfect way after collision to strike the next ball, and then the other ball, and observe the Newton's cradle. If there is an angle and the force that is being exerted is being in a different angle rather than in an alignment, then it creates a problem in measurements, and of course the last ball wouldn't reach the height of the first ball that we released. Parameters regarding material. In a Newton's cradle, ideal balls are made out of material that is very elastic and of uniform density. Elasticity is a measure of a material's ability to deform and then return to its original shape without losing energy. very elastic materials lose little energy. Inelastic materials lose more energy, as it's well known. And yet the Cradle will move for longer with balls made of more elastic material. The material of the balls also affects the amount of the energy that is lost due to friction. With inelastic materials, the results wouldn't be the same. And of course, we wouldn't also have the conservation of energy. Now regarding the number. There is usually an odd number of balls, and that's very, very important and crucial. 5 and 7 being the most common. Though any number will work, that's unequivocal. The more the balls, the fewer notable collisions will be made, since more energy is lost through factors such as friction. Now, about air resistance, which is very important to take into consideration, the resistance posed to the balls by the air does affect the transmission of kinetic energy between collisions throughout the whole experiment. As we have more and more balls, after around 10 and 15 while we were conducting the experiment, we faced some difficulties in measuring multiple differences in the collisions and also be able to make extrapolations. That's why it works like this. So now here is the setup of our experiment. Again, this is a direction that is not in perfect alignment. Of course, we cannot observe our hypothesis and of course the experimental data. Of course, this image shows what the perfect alignment is, and in this case, the Newton's Cradle will work perfectly. Here are some graphs about experimental results. Now, here, as you can see in the first, image, it's bounces versus number balls, and here you can see our measurements, the blue dots. But however, when we increase that by 2.2 centimeters, we see that bounces are significantly increased. Although you can see that the line can be almost identical as this, there is of course a significant difference between this kind of, let's say, propagation between the first. Now, another graph with regards to x-axis and seconds. It's almost an exponential line, which shows but it's our best fit line, in other words. Here you can see again the blue dots that we have measured. Of course, there are statistical errors in each time. That's why I'm not perfectly aligned. Whereas the next image, you can see the bounces and how that it loses energy in a period of time. So have more robust, let's say, oscillations that are getting milder and milder as time passes. Now, our conclusions. The number of oscillations the system completes is heavily dependent on the amount of the spheres in the system. The fewer the spheres are, the longer the system oscillates. There are less energy losses, which is very, very important to know, and the heat exchanges are less, and elastic deflection as well. 2. Dropping the balls from a slightly different height, as in the previous case, so greatly affects the number of oscillations. As the oscillations increase, larger amount of potential energy. Basically, all that is sold to a large amount of potential energy because it is stored in greater degree, and that's why it can transfer and transform into kinetic energy and transfer to the other balls. So greater potential energy is more efficient in measuring the results with regards to Newton's Cradles. Now the third is that not perfectly aligned spheres lead to significantly reduced oscillations. Now, the fact that the number of oscillations is highly increased where there are two spheres indicates that a large amount of energy is lost due to external factors such as friction. So, thank you for your attention.
So thank you for your report. The first question is, do you have any quantitative prediction for the motion of the ball?
Yes, we have
Quantitative. Yes or no?
yes, we have quantitative predictions with regards to numbers, what specifically.
Right, and did you plot these against your experimental envelope?
Yes, we tried to plot that. As you can see, some those blue dots are some of our measurements.
Okay, makes sense. And can you please quickly list all the dissipated forces in your system? Can you quickly list all the dissipated forces in your system?
Yes, the first of being exerted, of course, are the gravitational energy, the gravitational force. Of course, it's the resistance that's being exerted to the system, and of course, the force that's being exerted between the balls.
Can you please switch?
And of course, the tension from the connecting rod.
Can you please switch to the slide where you plotted the distance between the balls against time? I would like to know how you obtained this plot.
Yes, this
is
one,
graph number 2, yes.
this or this one?
This is
This one or this one?
second one.
The second one. How did I plot that?
How did you obtain it?
How did I obtain
Is
that?
that from literature?
Yeah, it was very reasonable. So we conducted the experiment, and we approached approximately in the first place. And as time passes, we try to plot that as oscillation are getting fewer and fewer.
I see, but how did you obtain that graph? Where did
Obtain
you
that
get
graph through a mathematical program that I put the values in, and the graph was schemed, let's say.
Was the strain in your Newton's cradle always taut?
Always.
Taut. Was there always tension in the strain?
There's tension in the string when it's being released, and of course the string exerts this force.
Is it
on the
always
ball.
in tension?
No, it's not always in tension. Of course, yeah, it's always in tension. Yes.
How did you make sure your system is aligned? number 15, Newton's cradle. Let's have a look at the problem state. It says the oscillations of a Newton's cradle will gradually decay until the spheres come to rest. Investigate how the rate of decay of a Newton's cradle depends on relevant parameters, such as the number, material, and alignment of the spheres. So the tasks we can derive from this problem statement are, first, to construct a well-controlled experimental setup with accurate and precise alignment to vary the relevant parameters. Then, we should derive a theoretical model to account for the collision mechanics of the system. Then, we should extend the theoretical model to account for other dissipated forces acting on the system to obtain a final equation of motion. And finally, we should experimentally verify the theoretical model by varying the relevant parameters as stated in the problem statement. So first, a summary of the report. The report began with a qualitative explanation of the phenomenon, and then went on to a brief analysis of the conservation of energy and momentum technologies. And then they had a very brief experimental comparison with their theory. So some merits of this presentation were that they have a qualitative description with the conservation of momentum and energy, and they had a qualitative description of the dissipated forces acting on the system, with importance put on the alignment with increasing the decay. However, there are many possible next steps, as the entire report is lacking any quantitative prediction, and the only one that was given was obtained from literature. Additionally, there was missed accounts for other dissipated forces acting on the system, which we hypothesized could be the pivot friction, air drag, and the viscoelastic decay from the collision itself. So we believe the possible next step should be to begin to develop a theoretical prediction to model this. In addition, they should improve their experimental setup to isolate the decay from each parameter to experimentally verify a theoretical prediction more accurately. Finally, I believe it is important in the report to make the equations governing the one graph that they showed more clear so that it's easier to understand. So I would like to invite the reporter up for the discussion. So first, an overview of the discussion. Sorry, can you revert the time? Yeah. What I said. So first, an overview of the discussion. So I would like to go over potential ways to model the contact mechanics of the system, and then how to model the other dissipated forces acting on the system, how to model potential alignments of the system, and then improve the experimental setup. So, to make the reporter up. So, can you please switch to that slide with the theoretical graph again that you obtained? I would like to know which equations you used to obtain that graph. Yes, that one here.
That one?
How did you plot this graph?
You mean this one?
Yes.
Of course, because it's long installation, that's why we used I measured first of all the collision, I measured collision, and by that of course by applying the special law of momentum, and then the velocity that I found, because harmonic installation I plotted in that way.
Do you have the equation of motion for this?
Yeah, first of all, you want me to write that?
Can you write your whole equation of motion?
Yeah. First of all, I applied the Bain initial equals final in order for the conservation of momentum, and by the and this is being described by this equation.
Like, what basic principle did you use to derive this? Like, where is the equation for this?
It's the
I see. So this equation here.
the equation installation.
Right. So this equation here looks quite similar to an underdamped system. Is that what you're assuming here?
First of all, it's not only an underdamped system. No, it's not only. No, it's not.
I strongly disagree with this because this equation here would model it underdamped. However, that assumes that from the collision itself, it's not losing any
There are
energy.
cases that you can be overdamped, damped, or underdamped, and it depends on the zeta factor you have, whether it's greater than 1 or
Right,
equals
right.
1, or less than 1.
Right, but in this, you're having discrete energy losses during the collision itself. So I don't think you can model it as a simple underdamped system. So I would like to propose an alternate way to perhaps model the collision. Have you looked into Hertzian contact mechanics? So I would like to propose an alternate way to look at the collision,
Yeah.
which may prove to be more accurate because I don't see a
No,
constant
it's quite accurate
Can I
because
see the prediction? Like prediction versus experiment?
the prediction, here are my measurements. The predictions were accurate were identical as my measurements. You mean,
Like, do you have like a plot of like your I guess angle versus like time, where you have like your theory and then your experimental like thoughts or any verification?
yeah, it's for example, in this case, yeah, I released from an angle of 90 degrees. I tested in an angle.
Right. You tested all that. Did you verify?
Of course, I verified that. If you see this this graph here, and for example, this oscillation time versus number of the balls, bounce versus number of the balls. Here's the plot with regards to the x-axis and the seconds that are passing.
So I believe it's actually important to clarify the second graph you have. I believe that
I clarified before it's a decreasing oscillation because as you release, because this is not conducting in idealistic system. That's why in this case you have a decreasing oscillation, which means basically it's a harmonic oscillation. It's decreasing as the time passes. So that's why it's
I
being
believe
plotted.
that the paper you obtained this from is called Walking Newton's Cradle, and it does not use this equation of motion. Instead, it models the force of contact using Hertzian contact mechanics. So if we have two balls here, and they have a certain compression or overlap, like denoted by this, then the force of contact between the two balls, would you go to write this out for me?
The force of basically that's being
So like if you have two balls with a small amount of compression, would you be able to let's call it epsilon? Would you be able to tell me the force of the force that the two balls exert on each other?
the force is being exerted is equal and opposite to the direction the force is being exerted from this ball to this ball.
Right. But would you be able to tell me
specific.
exactly how much force?
It depends on where you release the object, from what height you release the object, and what angle you release the object.
I would actually like to. I actually disagree with you. Based on Hertzian contact mechanics, which is where you got that graph from, I believe that the force of contact between the two would actually be given by your Young's modulus times root 2r over 3, 1 minus the Poisson ratio squared, times the overlap or compression to the power of 3 over 2. I believe this is the actual formula modeled by that graph there.
Yeah, can you define the epsilon?
Epsilon is the overlap, r is the radius of the ball, and E is the Young's modulus, and mu
Which is
is
the force that is being exerted on this. Yeah,
right. So this might
but
allow you to.
depends. Yeah, as I said before, but it depends on the height you release that.
Right.
Yeah.
Right. So it actually doesn't depend on the height, only depends on the amount of overlap between the two balls. So just by taking to this into
Depending on what you're talking about in elastic material and elastic material.
Right.
Yeah, are you talking about an elastic?
This accounts for any type of material. Because it's Young's modulus accounts for its elasticity.
Yeah, but what about inelasticity?
Then this
Wasn't
goes to a
taking-
time.
But it wasn't taking into consideration.
Okay, I would like to move on now. So during the collision itself, do you have any way to model the dissipated force acting during the collision?
Of course, as I said before, the force is being exerted, first of all, we have the momentum, so there is the force being exerted due to the fact of collision. There's also the gravitational force that's being exerted, and third of all, there is tension that's being exerted from the string that's being attached to the ball.
Right. Okay. Like during the collision itself, due to the compression, I believe if you use the same theory that the paper used, you would actually obtain something like alpha times the time derivative of the compression to the power of 3 over 2. Do you agree with this?
The time derivative
Of the compression to the 3 over 2. This is simply
Well,
derived from Hertzian contact mechanics.
where alpha is defined as.
Alpha is defined as an experimentally determined coefficient.
Yeah.
Do you agree with this?
Yeah.
So I believe if you use this model, you might be able to construct an accurate model for the actual collision itself. Now, moving on to our next point, what do you think are the other dissipative forces acting on this?
I told you before and explained that before. Of course, there's the gravitational force, the the tension of the string.
Like, do you account for tension of the string as a dissipated force?
There is a force that being inserted from the string on the ball. Yeah.
Is that a dissipated force?
Not
Like dissipated force essentially means taking energy out of the system. You think the tension force is taking energy out of the
it's
system?
not taking energy out.
Right. So what are the different things that are taking the energy out? I believe air drag for sure, right?
Yes, of course, there is this I mentioned before. You asked me before.
Right. And what else? Is there anything else?
Can you define here what's the force from the air resistance is?
Right. What is the Reynolds number here?
Can you define what's the air resistance force?
Right. So depending on the Reynolds number, it would either be a
Can
linear
you write
or
the
quadratic.
air
Right.
resistance force?
So if the Reynolds number is higher than about 2,300, it can actually be modeled as afro A C D.
Can you write please the force of the air resistance?
Yes, this is the force of the air resistance.
No, it cannot only be modeled like that. It can also be modeled like where bad is an
Right,
ideal
and
number.
this would be a more laminar flow region, right?
In this case, depending on the bag or the body of the bag.
I also think you might want to take into account the friction at the point of contact when you're
It's
spinning.
being taken into account.
How did you take that into account?
I took that into account, first of all, by measuring discrepancies in my results. In other words, I used different kinds of probes, strings, let's say, and I measured based on the density of sometimes of the weight that of course it can be taken into consideration, how the discrepancies in my results can be defined and I can observe.
So because your string is actually fixed at this point and fixed at another bar and another point outside the plane,
You mean on the joystick?
your string is actually twisting a bit here. So I believe you can actually model this or experimentally determine the friction from the pivot point due to the rotation, the torsional rotation of the string by putting your system inside a vacuum chamber perhaps. And then so you eliminate air drag and all the other dissipated forces. And by watching the decay of one ball swinging in a vacuum chamber, perhaps you can determine the amount of pivot friction acting on the
But
system.
according to the description of the problem, there is no indication that it was conduct the experiment into a vacuum. If you conduct it through the vacuum and
I have, yes.
How do you do
However, this is not about my experiment. However, I would like to say
No,
I
because
have-
that's soft particle that cannot be.
No, the reason I'm saying this because if you were to do like a torque balance on the system, you would essentially get your torque from contact minus your torque from viscoelastic decay, right? Minus your torque from air drag, minus your torque from your pivot friction, essentially. Now, air drag can be determined from here. However, you need to still fit CD because you might have string drag, right? This can also be fit from K can be determined. Well, this can be determined just from the properties of your material. However, to fit the pivot friction, you would need to eliminate all the others. So, by putting your whole system in, perhaps like eliminating air resistance, putting it in a vacuum chamber, perhaps you can improve your experiments.
Yeah, but I agree with this because it's an idea that it will come down to a different vacuum. Of course, it's much easier, but in our case, there wasn't any suggestion in the problem that we should happen like that in the
The problem asks you to investigate the rate of decay. I think by separating out each component of the decay, you can accurately determine how the rate of decay depends on the relevant parameters. Anyways, moving on. How did you align your system? How did you align your balls? So
I
if you
will
have
align the balls using,
like if these are your balls, how did you make sure that they're all aligned this way?
of course, while in the experiment we had some statistical errors, but we tried to do that using a laser beam that
Right. I would like to suggest a potentially alternate way where you actually use the capacity. You measure the capacitance between the metal plate and your ball.
The opponent need to summarize this concept.
So during our discussion, we went over potential so we discovered that there was no, the quantitative model was not clarified during the presentation. And I believe that the graph that shows their only quantitative prediction is derived from a paper based on Hertzian contact mechanics, which I believe the assumptions of Hertzian contact mechanics are accurate for this system. However, and then during the discussion, we went over possible methods of modeling the collision mechanics and modeling the other dissipated forces acting on it, including the air resistance and the pivot friction. In addition, I would have liked to discuss how to align the balls better using a capacitance method, where you measure the capacitance between the metal plate and the balls to better align it. And I believe that is everything we have discussed in this case.
a question from the viewer.
Alright, so first to the reporter, how was your dropping height in your experiments controlled?
What's my dropping height?
How was it controlled?
How was
Also-
control? Yeah, we used like a laser beam that measures the height from the point that we release the object to the ground.
So you used a laser. Did you hold or drag off the ball with your hand?
There was statistical error when I released it using my hand. But of course, I tried to minimize that using the results that I extrapolated from the laser beam that measured the height.
How many repetitions of each?
Around 20 to 22.
Alright, I noticed that you didn't present any error bars. Do you have any idea of the
There
approximation
are.
of your results?
As you can see here, the red dot and the blue dots I explained before.
Yeah,
here.
but you have no idea about the error. Is that correct?
Yeah, I have idea about the errors, and as I told you before, there was some statistical errors because
Yeah,
it's
but you have not placed them in your presentation. You have no
this is the
quantitative
best
idea.
fit line as you can see,
Alright.
and so the
So,
description.
to the opponents, is it true that the coefficient of restitution depends on velocity?
In this case, I believe it's yes.
And why is that?
Because, well, it depends on which model you're using. For a limited domain of velocities, it is relatively constant. However, if you increase this domain for higher amounts of compression, then it would not be a constant.
And to the reporter, how did you control the ball's alignment in your experiment? Talk about this being relevant. So
There were two procedures, one using wood instincts, and the second one is through laser beams that measure the height.
did you notice any vibrations in your frame of your Cradle?
Vibrations are, of course, while there are being the forces are being set between the balls, there are some vibrations that are being released in the form of sound.
In the frame or in the frame. Yeah. So to the opponent, what's the most important experimental improvement that you would give to our
I think
idea?
separating the different dissipated forces and then analyzing them on their own. I think the best way to improve this is actually to quantify the material properties of it and to align the balls better and to quantify the pivot friction in the system.
Alright, and then to you, the reporter again. Did you check the deviations between mass in your different balls in your Cradle?
I messed up in my report and you paid attention, and as I told you before, we were so careful to use masses that were of the same quantity.
So you have been weighing your different balls?
I
or
think
balls
what?
separately? Have you weighed your balls separately that you use in your Cradles too?
Yeah,
Alright.
use different masses, different
You have,
sizes.
yes,
Yeah.
thank you.
Perfect.
Onshage, and I will be reviewing this session for Team Sweden. So we'll start with the presentation summary. If we go into theory, we did see a defined and demonstrated phenomenon that was done by the Greece team. He mentioned the importance of perfect alignment. However, he did not talk about the losses from the breakup of the line that he demonstrated in his videos he showed in the beginning, where his balls in the line, the ones that weren't swung out, they had a distance between them. He didn't talk about how this would affect the phenomenon. He also had no theoretical model incorporating the losses. He had no quantitative explanation for how much decay we would see. Over to experiments, he used a cradle with double strings to increase the alignment, or the precision of the alignment to make this better. However, he did not look at different materials. He did not look at how elastic his strings were, which I believe is important, because if you have an elastic string, of course, as it goes down, the tension force on the string would increase, and so the alignment would be less accurate, because the string would actually increase in length as it went to the downward point of collision. He did not look at the friction force between the frame where the strings are attached to the cradle either. And he released his balls by hand, although he did use a laser device in order to measure error. As for his conclusions, he investigated the number of bounces and the oscillation time. However, he had no quantitative theory and experiment comparison, and small range of experiments and no error quantification. So if we move over to the opposition, to the pros, he pointed out the lack of theoretical model and some distributive forces, pivot friction and airbag. He brought up Hertz's contact theory, which we agree could be applicable in this experiment. And he also had some suggestions for controlling the alignment. However, he did not clarify several things about the setup: release mechanism, repetitions, error analysis, etc. He did point out about the vacuum chamber, which would be rather impractical, since the friction force between the wire and the frame of the cradle is so small that it's almost possible to exclude this fact as a factor. That experiment would be very happy just to watch this one small effect. So over to the clashes. The first clash, the opponent asked how the graph number 2 was obtained, and then the reporter drew this exponential decay, which it was overdamped. However, that is not corresponding to the waveform we saw in the image, and therefore the opponent went in and defined a better model using this Hertz contact theory. And we agree with the opponent that the graph that the Greece team presented does not follow the same waveform. But we believe that the coefficient of restitution in John's models should have been investigated experimentally to model the amount of bounces. So the second clash, what are all the dissipative forces in the system? And then you mentioned airbag and string friction. And the reporter said that airbag is proportional to velocity. However, we agree with the opponent that it's most likely rather proportional to the velocity squared. So on to some missed physics. As I mentioned, we didn't actually look at how the breaking up of the line affects the phenomenon and the decay rate, because when these balls are separated, we will have multiple collisions in one swing, in one oscillation. And this would be a very important factor, as this is one of the major energy losses. And we also had no discussion about the material of the balls, although we did talk about the Young's modulus effect. We did not have any experimental data showing this effect. Thank you very much.
Concluding remarks from the reporter.
Thanks to one more perspective discussion that I had with the opponent, and thanks for the comments of the reviewer. Now, for the conclusion, we strongly believe that we included as many as regarding to graphs and all the stuff that we needed were included and were shown here. In addition to this, I'd like to say to the opponent that the suggestion about the vacuum it is quite reasonable, and that could also be performed Moon, Mars, whatever any planet that a resisting substrate. However, that was not our case because we wanted to know how the Newton's Cradle performs at its best in some specific given environmental conditions. And also, with regards to dissipative forces, in this case, relatively the energy is being conserved. However, there are some cases that there are some losses from the point of from a given freedom of a system to another degree. However, generally the energy is conserved. So we saw and explained Newton's Cradle in depth and thoroughly.
Question from the juror. Anyone of the jurors like to ask a question?
Can you bring up the graph that everyone's talking about? Number 2. Can you explain why?
Which graph? First of
The second one. Can you explain why the distance between it is the distance between the two balls?
What is it?
On your axis,
Yeah.
you've got your y-axis as the distance between the two balls.
Yeah.
Can you explain the setup of this experiment?
Our setup. Basically, before we had the Newton's Cradle, so we released that from a specific height that we measured relatively from the ground to a specific height. So we measured that using a laser beam, which is used as for measurement. So that's why we were able to define the distance
Between the two balls.
Yeah.
So you measure the height for the distance.
Yeah, we measure the height that we released the ball, and through this way, yeah.
And so, how many balls are in your cradle?
In my case, well, when I conducted the experiment, I used 5 balls, 7 balls, and 9 balls.
And do you think that's the graph that you gave in that situation?
This situation refers to a ball, to a case that we use only 5 or 7 balls.
Okay.
Can you go back to some of your experimental plots? This one. So, no. So what exactly is the bounds?
Bounces are, as I said before, in my case I used 5 or 7 balls. So those are the bounces that you can see. So when I released that from a specific height, it had, right now, it had 25, this is bounces versus numbers of balls. So 25, 15.
So how do you define the bounds? What's one bounds?
One bounce is when the one ball is colliding with another ball.
So yeah, I have
Yeah.
10 balls. That means if it goes through all of them, that's 10, or is it 1?
It's 10.
It's 10.
It's 1. It's 1, sorry.
Okay. And if you like leave it a long time, how does it look like, the motion? Does it just like move these at the end? And
Because it's not conducting to ideal conditions, the selected in a way drawn are decreasing. That's why energy is being lost through a period of time. So that's why it gets.
so those inner balls are always staying in the place, and only those outer balls are swinging, right?
Yeah,
Right,
but
in experiment.
yeah, that could be the
all the
case.
time.
That would be the case of an ideal system. In this
Right.
case, because we conduct that into reasonable environmental conditions like this, of course we cannot observe that. Some balls could move beside it.
Okay.
So what is this oscillation pattern that you put on the graph? What's the definition of your oscillation time?
The oscillation time is basically the amount of time that it takes from the one ball to hit another ball until the other ball, the last ball comes to the relatively the same height that released the first ball. This is oscillation time.
But it's like 40 seconds.
It's actually the time needed for the whole phenomenon to stop. So every time it goes to a specific height, it's slower than the previous height. So until it stops, it's the general time.
And one question for the opponents. So for these graphs, can you just like positively explain why is the trend always downward? So if I increase the number of balls, number of bounces goes down. Can you just like put some, physical explanation of this?
There's no number of bounces before it stops, right?
So why does it decrease if I increase the number of balls?
So if you increase the number of balls, essentially the energy has to be transferred between all balls, and then it must compress at each. And when they compress at each, it's the same force that's still applied, but because it's through more balls and more compressions, more energy is dissipated.
Okay.
If I may, I would like to add to that we also have this breaking of the line effect, where we actually don't observe the balls being perfectly in contact with each other, the line. And so because they are at a distance, there will be multiple collisions, and not just one single collision with a stationary line.
Thank you very much.